Hello everyone, welcome to the lecture series of Theory of Computation. In the last lecture we learned about the basic foundational blocks of TOC, that is what are alphabets, what are symbols, what are strings and what are languages. Let's continue the languages part in today's lecture. So the next thing in language is calculating the reverse function. So what do we mean by reverse function is that if A is any word in some language L, then the reverse of A is the same string of the letters spelled backwards called the reverse of A, even if this backward string is not a word in L. So it says that if there is any string that belongs to my language L and if I calculate the reverse of that word, right, then it may be a possibility that the reverse of that word may not belong to the language L. Like for example, let's say if this is my string that is belonging to my language L, right? Now if I calculate the reverse of this, then it will be the same string only, right? Similarly, if I calculate the reverse of AB, then it comes out to be BA, right? Now for instance, suppose my language is any finite string of alphabet or letters, any finite string of alphabet letters that if it has length more than 1, then it should not start with a 0, right? For example, my alphabet is this 0, 1, 2, 3, so on up to 9, right? The language says that it can be any finite string that can be formed from these alphabet letters, and if it has length more than 1, if it has length more than this is length more than 1, then it should not start with a 0, right? For example, let's say if single 0 can belong to the language, but if the length of this string is more than 1, then it should not start with a 0. So let's, for instance, if I calculate the reverse of any string that's belonging to this language, let's say, so 140, let's take an example this. So this is my sample string 140. So it's belonging to my language L, right? It is a finite string of alphabet letters which are belonging to this alphabet, and it has length more than 1 and it is not starting with a 0. So it's satisfying all the conditions of my language L, and we say that this string belongs to my language. Now if I calculate the reverse of this, reverse of 140, this comes out to be 1041, right? Now this does not belong to my language L because the length of this string is more than 1 and it is starting with a 0. So it may be a possibility that if any word belongs to a language L, then the reverse of that particular string may not belong to the language L. So just like we have calculated the reverse of any string, similarly we can also find the palindrome of any string. So what do we mean by palindrome? So palindrome says that if, let's say, my alphabet is AB, right? So palindrome will be the null string for this particular alphabet and all strings X such that the reverse of that string should be equal to my original string. Then we say that that particular string is a palindrome, right? For example, what all palindromes can we form over this alphabet set? So we can say null empty string is definitely a palindrome, since the reverse of this particular string will be equal to lambda only. So yes, null string belongs to the palindrome, and single A belongs to palindrome, single B belongs to palindrome, double A belongs to palindrome, double B belongs to palindrome, triple A, ABA, BAB, BBB. So all these strings belongs to my palindrome. Now let's consider one more string. If I consider BAA, so the reverse of this particular string will be AAB, which is not equal to this reverse, so this is not a palindrome. So this will not belong to my this language of palindrome, right? Let's take another example. Suppose my S consists of this. S, we can call it either S or we can say it alphabet. So this is one or the same thing, right? Now, in the last lecture, we have learned about the Kleene closure. So if I try to find the Kleene closure of this particular alphabet S, then what will be the Kleene closure of this? It will consist of the empty string. Then it will consist of all the strings that are belonging to my original alphabet set. Like these two strings will belong to my S star or my Kleene closure. Then all the strings that we can form from the concatenation of these strings will belong to my S star, right? So what all strings can be formed from the concatenation of this? So we can form AAB, we can form BAA, we can form BBB, and so on. This is my S star, right? Similarly, let's take another example. Suppose S is A and AB. Now, if I calculate S star for this, so what will be my S star? It will consist of lambda. Then first it will consist of all the strings that are belonging to my original alphabet, that's A and AB. Now concatenation of all the strings that can be formed from these two strings taken in any particular order. So we can have AA, we can have AAA, we can have AAB, we can have 4 times A, and so on. Now if I have to check that whether any particular string will belong to my S star or not. Let's say for example I have to check ABAB. Now I have to check whether this particular string belongs to my S star or not. So how will we do that? Take the string that you want to check, which is A, B, A, B, and we can factorize it in the form such that it forms the factors which are in my original S. So in original S, I have two factors A and AB. So can we factorize this particular string in this form that I get the factors AB and A from it? Yes, I can form AB, I can form A, I can form AB from here. So all these three factors AB, A and AB belongs to S, and if all these three factors belong to S, then naturally their concatenation will belong to S star, right? So this is what we mean by S star, that it is nothing but the concatenation of the strings that are in my alphabet set S, right? So here we say that my factoring is unique. Since only unique, there is no other way to factorize this particular string in any different factors. So this here the factoring is unique. Let's take another example in which we say that the factoring is not unique. For example, if I take an example of consider S as XX and XXX, right? Now S star will consist of all lambda and all strings that consist of more than one X, right? Single X will not belong to my S star because it is definitely not belonging to S only. So if a string is not belonging to S only, then naturally it will not come in the S star. So it will contain lambda and all strings that consists of more than one X. More than one X. So can we rephrase it like it consists of X to the power N, where N can be either 0 and should not be 1, and it can be 2, 3, 4 up to so on. Right? We can factorize it like this. Now if I have to check that whether any particular string belongs to my S or not, let's say I have to check this 6 times X, right? Now in order to check that whether this belongs to S star or not, we have to make factors of it. So there are two ways I can factorize it. Either I can factorize it like this, or I can factorize it like this. Both XX and XXX are my factors in S. So naturally I can factorize this particular string in this way. So since there are two ways to factorize it like this, we say that the factoring is not unique. Factoring is not unique. Factoring is not unique, but the string definitely belongs to my S star because we can definitely factor make factors of this particular string that belongs to my S. So naturally this will belong to my S char, but here the factoring of this particular string is not unique. Let's say if I have two sets, S consists of A, B, AB, and T consists of A, B, BB, right? Now if I calculate S char, what will be S char? S char will be lambda. It will consist of all these strings that are belonging to my S, A, B, AB. Now any string that can be formed from the concatenation of these words. So we can have double A, we can have double B, we can have ABA, we can have BAB, and we can have number of different strings. Similarly, T star will consist of lambda, it will consist of A, it will consist of B, it will consist of BB, and it will consist of all the strings that can be formed from their concatenation, like it can have AB, it can have BBB, it can have ABB, and so on. So can we say that S char and T star are both the languages? S char and T star are nothing but languages that consists of all strings of A's and B's, all strings of A's and B's, right? I can form any string of A and B from all my S and also from my T. So basically S char and T char of these particular alphabet will consist of all the strings that can be formed from A and that can be formed from B. Even though the S and T of these two languages are different, still their S char and T char forms a language that is same. So just like we did about the S char, we have another terminology which is S plus. Now what do we mean by this is, let's say if my alphabet consists of X, then what will be my clean closure of this? It will be L, it will be lambda, it will be X, double X, triple X, and so on. Then my positive closure, this is my clean star, this is my positive closure. This will consist of all the strings that can be formed from this alphabet excluding the lambda. So excluding lambda, every string that can be formed from this alphabet will be part of my positive closure. So this is the difference between star and plus, that in star we include the null string also, but in plus we exclude the null string. So from this we come to another important conclusion which says that if S is a set of strings not including lambda, then S plus is the language S char but without the word lambda, right? So except for the word lambda, S plus and S char are exactly similar. The only difference is in terms of the word lambda. Now let's say if we say that S consists of X, right? It consists of this particular alphabet which is X. So here we can say that S plus is not equals to S char naturally, because this will contain lambda and this will exclude lambda. But let's say if S is a language, if my set S, which is a language, contains the word lambda only, like for example my alphabet or my set is containing the word lambda. Now if I calculate the S plus of this, so what will be S plus? Whenever we calculate either S plus or S char, first we include all those alphabets which are part of my alphabet only, right? So all those symbols which are part of my alphabet are automatically first included in my S plus and S char, and then later we start from the concatenation of all the strings that are there in my alphabet. So here, since lambda is part of the alphabet only, so it will naturally be present. then all the strings that can be formed from their concatenation. So we can have double X, we can have triple X, we can have 4 times X, and so on. Similarly, S star, it will contain first the strings that are part of my alphabet, then all the strings that can be formed from their concatenation. So here we can say that S plus is equivalent to S star. So the only condition in which both of them will be equal is when lambda is part of my alphabet only, then both S plus and S star will be equal. So this plus is nothing but we call it positive closure. Positive closure. So this is my Kleene closure, this is my Kleene closure star, and this plus is my positive closure. Now let's say if I have S as W1, W2, W3, then S plus will consist of, it will first contain these symbols as it is, and then all the words that can be formed from their concatenation, W1, W2, W2, W3, W1, W3, and the rest. Let's say W1 is equivalent to AA, W2 is equivalent to BB, and W3 is equivalent to lambda. Then in that case, S plus will contain the lambda because that is part of my alphabet only. So in this case, again S plus and S star will be equal because lambda is part of my alphabet only. From this, we come to another conclusion which says that from S we can derive the S star. Now no matter how many times we take the star of this, the result that we'll get will be exactly similar, right? So either I take S star and then take the closure of this, or I take 2 times closure of the same S. So this is exactly similar, right? Because S star is nothing but the concatenation of strings that are there in S. So no matter how many times I place star over this, how many times I do the concatenation of this, I'll get the same strings only. So this result is exactly similar, right? So we can prove it with the help of an example also, that for any set of strings, S star is equivalent to S double star. Let's take an example like S is suppose A, B. Now what will be S star? S star will be lambda. It will consist of A, B and all the other strings that can be formed from their concatenation. Right? Now if I take closure of this again, if I take S star and then star of this again, so basically of this I'm again taking the closure. So this will first consist of all the strings that are there in S star, A, lambda, A, B, AA, BB and so on, and rest all the strings that can be formed from their concatenation. If I have to prove that S star and S double star are equivalent or not, let's take any strings, let's say AABBA, BAAA and AABA, right? Now all the 3 strings, they are belonging to my S star. We can check. All these 3 strings belong to my S star. Now when I do their concatenation, it will form AA, BA, BAAA and AABA, right? Now just now we have seen that if we have to check that whether any particular string belongs to the language or not, we can factorize it, right? And if the factors of that particular string belongs to my original set, then we say that the string also belongs to my language. So if I make the factors of it, I will get like this. I will get 2 factors only, either A and either B. Now all these 3 factors, all these 2 factors A and B belongs to my S star. And if they are belonging to my S star, then naturally their concatenation will belong to the closure of this also. So this proves that S star and S double star are nothing but their equivalent. So we can write the proof of this particular statement like this also, that every word in S double star is made up of factors from S star only, that we have just seen. Every factor from S star is made up of factors from S, right? Therefore, every word that we have in S star is ultimately made up of factors from S only, right? Every word in S double star is nothing but made up of factors from S star. Every factor from S star is made up of the factors from S. So from transitivity rule, we can ultimately say that every word that we have in S star, S double star is nothing but made up of the factors from S only, right? So S double star is nothing but a subset of S star, and the vice versa is also true, that S star is a subset of S double star. So ultimately we can say that S star is equivalent to S double star. So this proves this statement. Coming to some questions now. So the first question says, consider the language S star where S consists of AA and B. Now how many words does this language have of length 4, of length 5, of length 6, and what can be said in general? So for that we have to find that first. So let's first consider length 0 words. So length 0 words are lambda, empty string. Then length 1 word, strings of length 1 is single string only, that's B. Then strings of length 2, we can have 2 strings of length 2, AA, BB. So here let's calculate the number. Length 0 string we have just 1, length 1 string we have just 1, length 2 strings we have 2, then length 3 strings. Now length 3 strings can be formed by the concatenation of the words in length 2 and length 1. AA, B, we can have BB, either 1 into 2 or either length 2 concatenated with length 1 or length 1 concatenated with length 2. So this will be AA. So I will have 3 strings only of length 3. Then let's calculate length 4. Length 4 strings can be formed by concatenating length 3 with length 1, 3 with 1, then we can concatenate 2 with itself, then we can concatenate 1 with 3. So we will have length 4 strings as AAAAA, length 2 concatenated with itself, then length 3 concatenated with length 1, which will form AABB. BBB is already a part, so we won't include it. BAAB. And 1 concatenated with 3. So we will have BAAB. BB is already a part. Then BBAA. So how many strings we have in total of length 4? So these two are similar only. So it will be counted once only. So we have 5 strings of length 4. So length 5 strings will be then AA, BAA, then BB, AA, AA, AB, then BB, AAB, then BAA, BB, then AABB. So that's it. These all strings will be of length 5. So there are 8 strings. Now can we guess a pattern from this? We can say that length 0 string is 1, length 1 string is 1, length 2 string is, if I add the length 0 strings plus length 1 strings, I'll get 2, 1 plus 1, 2. Then in order to find length 3 strings, I can add up with length 1 string and length 2 string, that will form 3. Then in order to find length 4 strings, I can add up length 2 plus length 3, 2 plus 3, that's 5. In order to find length 5 strings, I can add up length 3 plus length 4, that makes it 8. So what does it show? It shows that it's a Fibonacci pattern that's being forming over here. So in order to find any word length, it is nothing but number of words of length n minus 2 plus the number of words of length n minus 1. So if I have to find it, let's say further, it says length 6. So length 6 will be nothing but length 4 strings plus length 5 strings. So that will be 5 plus 8. I will have 13 words in total. Consider the language S star where X consists of double X and triple X. In how many ways can X19 be written as the product of the words in S? This means how many different factorizations are there of X19 into double X and triple X. Now how to go about with this one is, it says that S consists of double X and triple X, right? If I take it as D, represent this double X with D since it's a double, and represent this triple X with T since it's a triple. Now I have to form X19. So in how many different ways can X19 be formed? Either I can take it as, if I take 8 times double, then how many X I will get? I will get 16X. And if I take this triple one time, then how many X I will get? I will get 3X, right? So in total I will get 19X. So this is one way of writing it. Either take this double 8 times and take this triple 1 time, so I will get X19. This is one of the way. Another way is, if I can take this double 5 times, so how many X I will get? I will get 10X's. And the remaining are 9X's which can be formed by taking this triplet 3 times. This will give 9X. This is another way of writing it. Another factorization that I can have is, if I take this double 2 times, how many X I will get? I will get 4X. Remaining are 15X which can be formed by taking the triplet 5 times. 5 times triple. So this will form 15X. So again it will form 19X's. So these are the 3 ways in which X19 can be factorized. There is no other way in which I can write this X19, right? So 3 different factorizations are possible. Now it says, in how many ways can X19 be written as the product of the words in S? So it is asking, I have these 3 factorizations, and how many different ways it can be arranged. It can be arranged in many different ways, like in the first arrangement where I have 8 double and 1 triple. I can have first double here, then I can have the next triple, then I can have next double, then next again next double, then again next double, and so on. So this arrangement can be, order can be changed. Order can be changed the number of times. So this is nothing but we are talking about the combination. So when the order doesn't matter, we take the combination of this, which says that number of different ways of arranging it will be NCR, which is n factorial, n minus r factorial into r factorial. So for the first arrangement where I have 8 double and 1 triple, first arrangement where we have 8 double and 1 triple. So in how many different ways it can be arranged? Total there are 9. 8 plus 1, total there, and the value of n is 9 different arrangements. And in how many ways it can be done? N minus r into r factorial. So r is 1, n minus r will be 8 factorial, so this will be 9. From the second arrangement we have 5 double and 3 triple. So this is 8 factorial into 5 upon 5 factorial into 3 factorial, which comes out to be as 56. And from the third arrangement we have 2 double and 5 triple. We get 7 factorial upon 2 factorial into 5 factorial, which is 21. So it forms 9 plus 56 plus 21, which is 86 different arrangements are possible to factorize x to the power 19 as double x and triple x. Coming to the next question now, which says prove that if y cube is in palindrome, then so is y. So we know this obviously. If y cube is a palindrome, then y will also be a palindrome. Now how can we prove this? Let's say if any string is a palindrome, if a string is palindrome, here we can say y cube, right? Then deleting equal number of letters from both the ends leaves a palindrome only. So if this is y cube and this is a palindrome, then if I remove equal number of letters from both the ends, right? If I remove this first one and the last one, then I will be left with y, which is ultimately a palindrome only, right? So hence removing the front and the rear copy of y from y cube, which is palindrome, leaves the palindrome string y only. So this proves that this is y is a palindrome. Coming to the last question now, which says S is AB, BB and T is AB, BB and 4 times B. Show that S star and T star are equal. What principle does this illustrate? Now here we can clearly see that S is a subset of T, right? Now double B. This is the only word that is in T but not in S, right? So, but we can see that this double B belongs to S, right? So, if double B belongs to S, then 4 times B will belong to S star, since this can be formed from the concatenation of double B, right? So, if double B belongs to S, then naturally its concatenation with itself will belong to S star. So, from here we can say that T star is nothing but a subset of S star only, which proves that S star and T star are equivalent. So the only string that was extra in T was this string. Now, but this string can also be formed from the concatenation of the words in S. So naturally their star is also equivalent. So S star is equivalent to T star. So this proves this statement. So this was all about this video and the languages portion. In the next video, we'll start with the regular expressions. If you like this video, then do like and share my video and subscribe my channel. Thank you.